Hello, everyone, and welcome to Talk Nerdy. Today is Monday, November 15th, 2021, and I'm the host of the show, Cara Santa Maria. And before we dive into this week's episode, I do want to give those of you who make Talk Nerdy 100% free to download week after week a shout out. You can pledge your support at patreon.com/talknerdy. And as I mentioned last week, I have some new tiers available for you guys. So not only do you get access now to an ad-free version of the show for as little as a $2 pledge, you can also join the Discord server with your $10 pledge. And if you are either one of the coolest people in the universe or one of the coolest people in the galaxy, I also give you a shout out at the top of the show. This week, I want to thank Daniel Lang, Mary Neva, Rob Schreck, Brian Holden, Christopher Pitts, David J.E. Smith, Dudas Infinitas, Frederick Fast Markison, Gabriel Felipe Jaramillo Gonzalez, June Sapara, Leonard Prince, and Ulrika Hagman for their support of the show. And if you feel like your name should be called at the top, but I didn't, it might be because you didn't specify that you want to be in the tier that you're in. So make sure that not only is your pledge where it wants to be, but also that you've specified your tier so that you can get access to all of the great new perks. Again, learn more at patreon.com/talknerdy. All right, so let's talk about this week's show. So I had the opportunity to sit down with Dr. Arik Kershenbaum. He's a zoologist and a lecturer and fellow at Girton College, University of Cambridge. And he's done a bunch of field work on animal communication, which we discuss. He's studied wolves all over the U.S. He has also studied dolphins and, as we talk about in the show, hyraxes, and so many more. He's also a member of the International Board of Directors for Medi.org, which is a think tank on the topic of messaging extraterrestrial intelligence. And that's going to be a big part of what we talk about today. Yes, a zoologist, but also life and life elsewhere in the universe. His book is called The Zoologist's Guide to the Galaxy: What Animals on Earth Reveal About Aliens and Ourselves. So without any further ado, here he is, Dr. Arik Kershenbaum. Arik, thank you so much for joining me today.
So glad to be here.
Was my pronunciation okay that time?
It was good.
No, good. So I'm super excited to talk with you about your new book, The Zoologist's Guide to the Galaxy: What Animals on Earth Reveal About Aliens and Ourselves. This has, I've got to be honest, long been a really interesting topic to me that is often approached by scientists from wildly different disciplines. This idea of like, what is life and how do we define it and how does it operationalize, and would it be the same somewhere else? So I think just this concept that now we're coming at it from a zoological perspective, I'm just so excited to dive into our chat today.
Yeah, and it is different. You're right, because zoologists don't usually deal with these questions. We usually leave it to the biochemists and the people who ask questions like, what are the building blocks and what are the chemistries that work But no, I like to look at it also from a evolutionary and from an ecological point of view as well.
And you know what's funny is that I would say that most of the astrobiologists that I have spoken with on the show, I think I've had a couple astrobiologists on the show, although they have training, you're right, in biochemistry, they mostly came from like classical physics and cosmology and just, I think probably were inspired by these questions along their studies and so gathered more training. But very often I see this conversation coming from the physics side, which is like wildly different than the, like you said, evolutionary biology, ecology, anatomy and physiology, kind of the core life sciences of what it is to exist on planet Earth.
Yeah, and that's not surprising. I mean, it's the physics that's easy to measure, right? You look at planets, you look at stars, you've got a telescope, you've got a radio telescope, you can measure things, you can measure what chemicals are in the atmosphere. And that's why a lot of the experimental side of astrobiology has come from the physicists. And that's great. But at some point, when we do discover signs of life on other planets, then we are going to have to start thinking about the other dimensions, thinking about how the life evolved there, how it got there, what kinds of interactions exist between the different organisms that might exist on a planet.
So let's talk first. I guess before we start to get extraterrestrial, let's talk first about, life on planet Earth. So you are a zoologist. You currently, I'm just looking at your bio here. You're currently lecturing at, how do you pronounce that? Is it Girton College?
That's right, yes.
Yeah, in Cambridge. And you've studied animal communication for a lot of your career. Tell me about how zoologists often find their sort of grooves and what types of specialties many researchers that come from a similar training background as you kind of fall into. Like why animal communication, and is that quite common for zoologists?
Hmm. Well, all zoologists are really, what we're really interested in is why questions, right? It's all about why. Why do some animals do this and other animals do that? Why do some animals have horns and other ones don't? So instead of just describing what we see,
Hmm.
it's all about those why questions. And, some people are interested in why particular cells grow the way that they do, and why some animals have sexual reproduction or asexual reproduction. And other people are interested in why some animals just communicate more than other ones. What is it that's driving that? What's the big difference? And yeah, everyone has their groove. It's true. And that usually comes from which of those why questions most grab you, are most appealing and most intriguing.
Got it. Got it. When I think about things like animal communication or basically just behavior in general, especially if we're talking about observing animals in the wild, in national parks, or even in, unfortunately, often we observe this kind of behavior in zoos and slightly less, I guess, natural settings. It's funny because my field, I come from psychology and neuroscience, and very often I see that this is a big interest area for like comparative psychologists, that they are very interested in looking at animal behavior to try and understand those why questions.
Yeah, and there's been for a while now a big interest in evolutionary psychology, which I think is a problematic concept in some ways, but you can't deny that a lot of behaviors are um, evolved to help animals manage in societies, manage interactions. Are you fighting with other animals? Are you friends with other animals? Do you have a dominance hierarchy in your group, and how do you relate to other individuals? And these problems that animals deal with are problems that humans deal with too. So there's certainly a lot of interesting stuff going on in animals that should interest psychologists as well.
Yeah, and it's funny because when you think about these why questions, the ones that really grab you and sort of take you out of the laboratory and into the field and really drive you to start digging deep into the mechanisms behind the why, um, it it really does take you to a plethora, I guess would be a good word to use, of different examples of those why. So, whereas some people dedicate their careers to really studying a particular species or maybe a particular genus and understanding a lot of the ins and outs of the behavior or the sort of idiosyncrasies of those particular species, you have looked at so many different animals to try and understand communication from a lot of different angles.
Yeah, that's right. I mean, even those zoologists and scientists who study a single species, of course, are still asking why questions. It's always about how did evolution operate to give these animals the characteristics that they have. But you're right. What really interests me is looking at across the range of animals and across the range of different kinds of niches and habitats and different ways of communicating. What's in common? What do they have in common? What are the sort of common constraints that are operating?
And I'm seeing even just in your bio that the like wolves in Yellowstone, dolphins, and hyraxes are highlighted, which makes me so happy. I love hyraxes. Living in the US, most people here don't know what hyraxes are. And you mentioned hyraxes in Galilee, and I had the opportunity to observe hyraxes in Namibia quite a few times. I didn't know that they sing. I've never heard them vocalize before. I've just seen them running around the rocks, and there they call them rock dassies, and they're such cool animals.
They really are, and they're incredible that they do sing such complex songs, and you can't, for the life of you, looking at them, you cannot imagine why they would bother to have such complex songs, but they do. And these are the kinds of questions that we have to ask. You observe something strange. Why is this little furry creature singing these incredibly complex songs? And these are the kinds of things we're out to answer.
And so, what are some, before we really get into this sort of astrobiology component of this, or I don't even know if that's the right word to use, but this idea, this larger questions about life and how do we define life and how would life look if it evolved under different constraints? What are some of these kind of bigger questions that you've asked in your career so far and have been able to find, some answers to?
Well, one of the big questions, certainly when it comes to communication, is where does complexity come from? Why communicate in a complex way? Birds also sing very complex songs sometimes, and they really don't need to. Okay, they're not actually saying all that much. So where's all this coming from? What's driving all of this? And when you ask questions like that, and you look into what's in common, what do all these complex singing creatures have in common? Some of the answers are quite universal, actually. They're the kind of answers that will apply on other planets as well, because they're questions of things like, how do you maximize efficiency? How do you get a message across? How do you impress the female birds the most while not expending too much energy? And these are things that the answer is often complexity, and those same answers should apply to birds singing on other planets as well.
Right. And so much of that story, it seems, and tell me if I'm wrong, it seems is a very, very long story of quite random evolutionary pressure. So although things seem at the surface sometimes quite fantastic or quite over the top, like when we're talking about birdsong, or very often we talk about plumage, right? And how kind of intense birds' plumage can become. And for as far as we know, mating rituals. It really comes down to this idea of evolutionary pressures, right? Of bottlenecks, of different kind of fits and starts and twists and turns in the evolutionary story in which nature put the pressures on for these different creatures to survive and to thrive, and sometimes the strategies are quite kind of creative that we find to help with that survival.
Yeah, and yet we do see similar strategies cropping up again and again. Birds have colorful feathers, birds have complex song, but these are both things that have evolved over and over again repeatedly. It's not all coming from one source. So what we learn is that over the massive evolutionary time, I mean, really, animals and other organisms have been on this planet for so unimaginably long that that these characteristics that just keep coming back, keep occurring again and again and again, using sound, using colorful colors on feathers or skin to send messages. These things keep cropping up because they are just the effective and efficient way to solve the same problem that keeps coming up over and over again.
It's funny because when we think about, science fiction, or we think about these very human inventions through story, through art, of what an extraterrestrial ecology might look like, oftentimes the star of the story is the humanoid, right? So it's whatever version of ourselves we're encountering on another planet. We don't often see examples. There are, of course, exceptions to this, but we don't often see examples of biodiversity when we think about life on other planets, or films that really, and part of that is probably simply because it would be very expensive to do. And some, Avatar-esque stories have really captured that portion of this astrobiological problem. But I do think we often think about, well, what's like the human version of life somewhere else?
Right. And what's missing there, of course, is that if humanoids or the equivalent of humanoids exist on another planet, they didn't pop into existence. They came from and from within a rich and diverse ecosystem. You can't have intelligent technological humanoids unless they are coming out of a really complex environment and a complex web of interactions between different species. So that stuff that we don't see in the sci-fi, that's actually what's driving the evolution of intelligence, in fact.
Yeah, it's so interesting, and it's very often not a part of the story, which is a huge bummer because I think we're missing out on number one, something very visual and beautiful that could be part of the science fiction world. But number two, I think an important part of our understanding of our place in the universe. It's just a recapitulation of, I think, sometimes this very human centric, narcissistic kind of post life view. It's very Wall-E, if you've ever seen that film. It's quite sad and post-apocalyptic, the way that we often show what life on other planets could look like.
And yet, on the other hand, it's actually quite uplifting because if we know that life on other planets is quite likely to have forests and oceans full of creatures. I mean, forests, not necessarily trees, but this complex, deep, diverse set of organisms that are all interacting together and eating each other and running away from each other and cooperating with each other. And that's something I'd really like to see. I know I won't, but I would like to.
Yeah. And so it really, I think, it leads us to this very important question. And, a question that often that doesn't, I don't think, you can correct me if I'm off base here, but I don't think has a well-defined answer, which is, what is life? How do we, what is life versus what is not life? Because often we throw the wrenches in the equation, like, what is a virus? Is a virus alive? Or at what point do sort of an assemblage of molecular machines or an assemblage of certain types of molecules go from being not life to life? What is the essence of life, and how do we define that?
Well, people do try, of course, and they have to try because when you're building instruments to look for life, then you need to know what you're looking for. So I see the reason behind that, and it is true. When we mustn't forget that life on Earth existed for about 2 billion years, and it was really quite boring, right? It was really quite simple, and possibly alien explorers coming to Earth might look at it and say, "Is that life? Maybe it is. Maybe it isn't." But then, about 1 billion years ago, things started to change and it just became obvious. All right, let's be honest. If we go to any alien world, which has any level of complexity in the organism, anything more than a bacterium equivalent, we'll know it's life. It will be obvious. And it'll be obvious because of those interactions and that diversity and that ecosystem.
Right. So it's probably not so much a question, like an astrobiological question of, is that rock actually alive or a creature? Is that thing that I think might be a, I don't know if it's animate or inanimate. I don't know if that multi sort of complex thing is living versus not living. It's probably more at the unicellular microscopic level at which there's some confusion or the definitions become more wiggly.
I think so. I think so because I think, and this is something that's often forgotten, is that if you were to land on another planet and see some kind of complex organism, some kind of animal or plant, or even anything like as simple as an insect or a fungus, you would that organism could not have evolved in isolation. Right? Complexity in life arises as a result of a diverse set of challenges that life faces. And those challenges come from other organisms. So it's precisely that interaction, it's precisely that web of interactions that's driving the very complexity of life itself. So you'd never land on a planet and just see one insect, right? It would always be in the context of an ecosystem.
Right. So even the planet where the first thing we saw was, I don't know, a bunch of sea sponges or barnacles or the equivalent, and we were like, uh-oh, don't know if they are alive or not. They would be within the context of a lot of other things that have the type of complexities that would, like you said, you just know it when you see it because they might be respiring or moving or metabolizing, or they'd be doing things that are indicative of life.
That's right. And they'd be interacting with each other because it's precisely the interaction between different species that's driving evolution, that's driving things to become more diverse and more complex.
And so, the truth of the matter is we're nowhere close to having the technological capabilities, or even, I think probably more importantly, it's not as much the technological capabilities, because we can do a lot of cool stuff with robots right now and go pretty far away. But, as human observers, our own bodies, our own biology thus far does not really allow us to travel in space very far. Space is quite dangerous for us. It's quite, I wouldn't say toxic is the right word, but the radiation is not good for us. And we haven't kind of figured out how to make space more healthy yet. So that said, very often the tools that we're using to try to detect life are really about chemical signatures, right? Or it's about, looking at the atmosphere of very far away potential planets, or bodies in other parts of away from us, and trying to understand what are the signals that are being put off within the atmosphere of this planet, and do those signals tell us anything about whether life exists?
Yeah, and it's frustrating. I know. I would love to take my binoculars, and go to an alien planet and look at the alien hyraxes, and that would be fantastic. But you're right. There's no realistic possibility of traveling to another solar system. But having said that, I mean, our instruments for probing the atmospheres of planets around other stars have improved so dramatically and continue to improve that I think we're really, we're getting close to the stage where we can start realistically expecting to discover things. And don't forget that there are planetary bodies in our own solar system that may be capable of supporting life. And I'm thinking of moons like Europa and Enceladus that have underground oceans that are eminently explorable within a human lifetime. So that's another thing to bear in mind. We don't know what's under the ice crust of either of these moons, and except that we know there's liquid water under there. So that's another interesting avenue.
And so kind of two questions come up for me with regards to what you just said. The first one having more to do with the tools that we're using to look at maybe extrasolar signatures. So, I'm hoping that maybe you can tell us a little bit more. And of course, this is coming from the perspective of a zoologist, but tell us a little bit more about what that means. What do these chemical signatures actually mean? What are we looking for? And how confident could we be? Because I know that this is also a part of the work that you do. Is it consulting, or are you actually on staff with Medi, or you're on the board of advisors for Medi? This idea of like, how do we message to these potential intelligent species? But first, we would have to find where they are. So I guess the first question is, what does it mean to search for signals of life without actually being able to investigate? To put boots on the ground.
Hmm. Well, there's two types of signals. There are technological signals coming from an advanced technological civilization, and then there's signs of life. And pretty much now, I mean, the real advances are being made in the search for signs of life. I'm sure you followed what happened with the phosphine signatures on Venus and the James Webb Telescope. There's just a lot of stuff going on at the moment to empower us to look more closely at what's happening on other planetary bodies, even outside our own solar system. And what they would be looking for, essentially chemicals in the atmosphere at the moment, is some kind of evidence of something that looks like metabolism. And the whole problem with the Venus phosphine situation was that here was the discovery of an unexpected chemical that couldn't be explained. And then the question is, well, can it be explained by metabolism, by some organism that's making this chemical? And without having much understanding of what kinds of organisms might be there, that's a difficult thing to do. But I think that we are lucky in one surprising respect, which is that although alien life could be very different from ours biochemically, there are some reasons to think it might not be. And the sorts of reasons are that the things that we're made of, water, carbon, mostly, they're very, very common in the universe. This is not rare stuff. We're not made out of really weird, rare stuff. We're made out of stuff that exists probably on at least one planet around every star in the solar system. So we can be looking at the atmospheres of these planets for the kinds of metabolic products that we might expect to be produced by life on Earth. So we could be wrong. There could be mistakes, like with the phosphine. That nothing that we know on Earth really metabolizes much to produce phosphine. But by and large, if we look for stuff that's like our own chemistry, then we're probably doing okay.
Yeah. And so
And then
the
and
other,
then there's a
oh,
question about the technology. That's
oh,
another.
right. Yeah, yeah, yeah.
Then that's another question, because
And
if you're
we keep having similar issues where it's like, oh, what is that signal? Oh, it's an FRB. Or what is the FRB? Oh, it turns out it's, just this type of planet that spins around, or, all these different things that we get very excited about signals. More often than not, these signals turn out to be just functions of the way that that a physical celestial body exists in space.
Yeah, and when searching for signals and signs of alien intelligence and technology, then we make a lot of assumptions about what kinds of things they might be sending. But we kind of rely on this idea that technology is going to be obvious, right? It's not like phosphine. It's not like finding methane or carbon dioxide in an atmosphere. It's going to be pretty obvious if you think about the signals that we're sending from Earth now. Just our radio and television broadcasts that are streaming out into space at the speed of light. Anyone looking at those would know perfectly well this is not a natural phenomenon. So that's kind of the basis on which we're working. And also, hopefully, if there are civilizations out there, maybe they're even trying to contact us, and then that would be even easier to recognize and decode.
I want to get to my other question in a second, but first, that just inspires me to ask you, like, how confident are you that intelligent life, and so I'm not just talking about like the building blocks or like very basic, that biochemical life that we discussed that happened 2 billion years ago. I have a high level of confidence that that's sort of happening in several places in the universe. I don't, I'm not really sure that I could tell you where that comes from, but just in all of the conversations that I've had with scientists over the years, the things that I've read, I feel pretty confident that there's sort of like a primordial soup out there and that it's probably happening, over and over. But in terms of sophisticated, intelligent, technological life at this very cross section in time, existing, being interested in reaching other beings like we are, and having the kind of technological capabilities to transverse space and time. How confident are you that that would actually occur?
Well, firstly, I think we need to make a distinction between intelligence and technological
Right.
intelligence, right? There's a lot of intelligent animals on this planet that aren't sending signals out into space. A friend
Mm-hmm.
of mine in the SETI Institute has the saying that they have, which is there are two kinds of organisms in the universe, folks and critters. Folks can build a radio telescope, and critters is everything else. Um, the idea there being that there may be very intelligent life elsewhere in the universe, but if it can't send us radio signals, we'll never know about it. So there is that distinction between intelligence and technology. But to your first question, I think I think, as you said, it's very likely that life exists in very, very many places in the galaxy for sure. Um, how advanced or how complex those ecosystems might be, that's a difficult question, because, like I said, life on Earth existed for 2 billion years out of the 3.5, right, that life has been around. Very, very, very simple. And in fact, the sort of organisms that we're familiar with today have only been around for about 500 million years out of 3.5. So you can imagine all of these planets with sort of bacterial slime on them and nothing else. But then again, we don't know how typical the course of evolution on Earth has been. Earth's a relatively young planet, and there are cosmic coincidences that have driven or perhaps impeded the course of evolution on Earth. So it's really, really hard to tell. I think that's a calculation that we won't be able to make convincingly until we have a bit more data on how many planets show these signs of metabolism. I think that will be a big help in trying to quantify those relationships. As for the existence of technological aliens, unfortunately, like you said, the chances of them existing in our slice of time, and not just our slice of time, remember, our slice of space time. So it's not enough that they are existing now, but they have to have been sending their signals sufficiently long ago that they've had time to cross from the other side of the galaxy and reach us.
Right, they might not even have to be existing now, but they had to be
Yeah.
existing then, right at that right moment.
And of course, the big problem that we see now is that technological creatures seem to be very bad for themselves. It's not at all clear how long a technological civilization exists on average, and it's not at all clear that our civilization will exist for very much longer. Certainly not at the way that people are not dealing with climate change at the moment. And it could be that in another 100, 200, 300 years, we simply won't be around as technological beings anymore. And unfortunately, that may be the case on very many planets.
Right. So the folks might be a flash in the pan, although the critters probably have staying power. And yeah, part of that is kind of self-induced. Yeah, it's interesting. I mean, it seems to be that the crux of this conundrum is that, we often hear we're dealing with an N of one, meaning, our sample size is only one. We know how things work here, and we use our understanding of how things work here to make oftentimes, I do think, very informed assumptions about how things might work in other places. But we obviously have huge gaps in our knowledge because we're coming from a very, shall I say, biased perspective.
Well, I'm not totally convinced by the n equals one argument, because I think we
Okay.
do have a lot of evidence here. We have a lot of evidence of how life works, how evolution works. We've come to a very good understanding, and really relatively recently, really only in the last few decades, of the kinds of mechanisms that are driving the diversity of life on Earth. And we see those mechanisms operating again and again and again, not once, but many, many, many times. And we see animals evolving wings to fly and legs to walk with, and colorful feathers and songs to advertise to their mates. And these phenomena, these characteristics, living in groups, living in societies and family groups and so on, these are not arising just because of something special on Earth. We know that, right? Right? We understand why animals live in groups, for instance. And animals don't live in groups because there's something special about Earth, right? That's just clear from the theory. We can see that, just as we can build a theory about how the inside of a star works without ever having been there. We can build a theory about why animals live in groups just from looking at animals on Earth. And so I think we have more of a theoretical foundation than is often appreciated.
Right, right. Because some of those, as you mentioned, many of the constraints that we're operating under are somewhat universal. We know about how um, uh, systems form. We know about how the universe formed from these basic molecules, how, gas and dust clustered. We know about these forces that are acting, and we know about a fair amount about the periodic table. There might be things missing. There might be things that exist in other places that we have yet to understand. But ultimately, a lot of these systemic sort of, I don't want to call them rules or laws, that gets very physics and very sort of away, I think, from biology. But these patterns, these emergent patterns, do seem to be somewhat reliable.
They do. We seem to see that on Earth. And another thing I think we need to bear in mind is that weird things will always happen. I have no doubt about that. There'll be planets in the galaxy with really weird life that's nothing like what I expected, that will prove me wrong completely. But they're going to be rare. Okay? The ordinary stuff is going to be common. The stuff that works the way that we understand that things work is going to be much more common. Like what I said about water and carbon, these are things that are common in the universe. Might there be silicon-based life forms? There might, but they're going to be extremely rare. It's the ordinary stuff that we're going to see again and again and again.
And so you're pretty confident that our experience is an example of the ordinary and not an example of the rare.
That would seem to be the case. And again, I'm not talking about the details of biochemistry. Is it likely that most planets in the galaxy will be occupied by organisms that produce phosphine when they metabolize? Possible. I don't consider that weird and wonderful. But I think that the general ideas about, for instance, that organisms must reproduce. If organisms don't reproduce, then there won't be natural selection. There won't be evolution. There won't be organisms. Organisms reproduce. Therefore, there are all kinds of family relationships. There's organisms that will have to care for their offspring so that they grow successfully and then can pass their heritable material down. That's just how natural selection works, and that's what we see here, and that's what we'll see in the vast majority of cases elsewhere too.
Right. And so, it brings me to this other big kind of burning question, which, as a zoologist, you're interested in animals, and we use animals as examples, right? We know that there are plants, we know that there's fungi, we know that there's the different forms of life. You have spent a lot of your career studying animals. And so this question may be a little bit out of your reference area, but what I'm, I guess, asking about are these precursors to animals. So this idea, you're not a microbiologist, but you are fundamentally interested in the animal story, the evolutionary story of animals, and also interested in this idea of extraterrestrial aliens, for example, animals in other places within the universe. And so I think this brings me to this basic question of, if what is likely more common and what is probably more uh, sampleable within the universe is this primordial kind of soup, are these early like archaebacteria or these early forms of less complex life. How would we know it when we saw it? Would we be able to recognize it?
Well, I'm going to challenge something here,
Sure,
and
thank you.
what animal, how we define animal
Hmm.
on Earth is quite strict, and it's quite clear. It's very obvious what are animals and what are not animals on Earth, and we just need to look at the evolutionary relationships between organisms, and you could tell an animal from a plant pretty easily most of the time. But that's a coincidence of evolution on Earth. Right? That's just the way that life evolved on Earth, and it could have gone different ways. And animals on other planets won't have had that evolutionary history. So I'm going to define animals differently. I'm going to define animals as organisms that move.
Okay.
And the reason that I do that is because movement would seem to be a really, really, really important feature in the evolutionary history on any planet. Once an organism it's moving in search of something. It's moving in search of energy. Usually, that energy could be light, so plants grow upwards. So in that sense, they move, but they're still accessing this static energy source. Organisms that move to gather energy precipitate a huge cascade of evolutionary consequences because they're eating something. They're eating someone else. And once you have organisms eating some other organisms, then they have to evolve defenses, and then the ones who are eating have to be better at eating, and so on. So a lot of the complexity in an ecosystem is driven by what I would call animals or moving organisms, even if they're not strictly speaking animals in the sense that we understand it on Earth. And moving organisms, so moving bacteria, are very old, right? They're very ancient. So even billions of years ago, there were bacteria that existed on Earth that probably moved and ate algae, and grazed on these algal mats. So that was already the start of this kind of cascade of effects that I'm talking about. And you'd notice that, right? If you went to a planet and you saw these little bacteria-like things crawling across a pond of algae and munching away, that would be obvious, even though they're essentially bacteria.
Interesting. So sort of the distinction that you're making is one of function more than of structure. Like you said, like an animal versus a plant, we know that, it's got a chloroplast, or, animals don't, or animals don't have cell walls, or, this is, this is how we metabolize. Our respiratory rate is much higher, blah, 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 blah. But really, if we were to look at even early aspects of complex evolution, like what was it called, endosymbiosis, this idea of how we've developed mitochondria, these more complex cellular organelles, had to do with being able to eat other things, or at least absorb other things. And in order to do that, you have to go to it somehow, you have to move towards it. So you're
That's
saying
right.
that if we were somewhere else, we might be able to observe this sort of motion, this activity, this action. But doesn't sometimes passive activity occur that can confuse us, like kelp in the waves, or things that look like they're moving, but really they're just reacting to environmental cues?
They can, but it's firstly that evolutionary role. So, what is the movement achieving? What is it? What are they moving for? Are they moving? Are they gaining energy by moving, and so on? And that should usually be fairly obvious. Of course, when we study animals on Earth and plants on Earth, we often come across traits that we think, well, I don't know why it's doing that. I can't really see the evolutionary benefit of that. So that does happen. But the other big giveaway, the other really, really big giveaway is that if you have moving animals, you'll have a web of interactions. Okay, you'll have the animals they're moving towards that are then moving away from them, and you'll have other animals that are taking advantage of that situation. And so, the moment that this kind of complex behavior evolves, there's a whole host of other phenomena that go with it that would just stand out. It would just be, it's not just, if it's just kelp moving in the waves, no one's paying any attention, no one's doing anything with that, you can assume it's some kind of passive motion. The moment someone is moving towards someone to eat them, then there's this whole host of other phenomena that spring into existence together with it.
Right. So I guess my observation of this sort of contextualization is one of interconnectivity. It's really one of an ecological mindset, which can feel, I think, to many people who don't, where this isn't their area of expertise, it can feel a little bit like, what's the word I'm looking for? Counterintuitive. I think we do tend to think sometimes in a reductionistic way, and sort of forcing ourselves out of those constraints and thinking in terms of the interconnectedness of all of these systems really does open up our ability to see patterns, to understand functionality that we might not see if we're used to thinking about an organism in a vacuum, if we're used to thinking about plucking it out of its environment and maybe studying it in a laboratory. That really, to see it existing within its immediate environment and all of these rich interactions is to understand the organism itself.
That's very true. I couldn't agree with that more, and I think it's one of the things that's really driven our understanding of animal behavior is to take it out of the lab and to see how animals really do interact in the environment. And when we look at explaining actually any evolutionary trait or any trait that any organism has, we like to say that there are four different reasons that an animal could have a particular trait that it has, and some of them are very mechanistic, to do with the sort of the underlying biochemical mechanism or the developmental mechanism. But the two ones that really interest zoologists the most, you can explain an animal's behavior or the characteristics that it has in terms of their functionality, so in terms of their benefit. You can look and see, okay, well, it has horns to protect it from predators. But you also have to take into account that it may just have horns because it's born to a lineage of animals with horns. That actually that
Yeah.
evolutionary background does set the constraints and does dictate the way that organisms are going to evolve and the kinds of traits that they're going to have. And just because something is beneficial, wheels, let's say, I mean, it's a famous example. Why don't any animals have wheels? And there may be many answers to that, but you can't understand it just in terms of, oh, wheels would be beneficial. You have to think about where they come from and how they would have evolved and how they could have come into being. Who was the ancestor who began on that path towards having wheeled a way of getting around. So yes, this is a multidimensional. These are all multidimensional questions.
Yeah, so it's not just about the interconnectivity with its ecological environment, but it's also how it's connected linearly throughout time. So, you think about human beings, like some humans have tails, because we used to have tails. And sometimes there's a little quirk of development that kind of like turns on certain genes and doesn't shut down the other genes. And then people are born with little tails because our ape ancestor, our ape like ancestors, we are apes. So, yes, humans are one of the great apes, but we had tails. Like apes have tails, and we just don't really use them. They didn't do us, any favors, or for whatever reason, we lost them over time. But the idea that a person might have a tail today, even though it has like literally no function, is totally understandable when you understand it in the context of evolution. It's like that famous question of why do men have nipples? When you really start to understand the evolutionary story, and you're not just looking at the story um, uh, of like you said, function or interconnectivity in this cross section of time, that opens up a lot more of those explanations to the why questions.
Mm. And here's the thing, which is that mechanism, exactly what you described, that's a general universal mechanism because organisms on another planet are going to evolve through natural selection. So they're going to evolve step by step, slowly, generation by generation, one after the other, small changes at each step. They're going to show the same sort of phenomena, right? They're going to show traits that perhaps were useful once, which no longer are, and gradually fade away from generation to generation, or maybe not, or maybe they're adapted into other useful traits. Feathers used to keep dinosaurs warm, and then some dinosaurs began to fly, and the feathers were really useful for flying. And now we think of feathers as being for flying, but that's not where they started out, and they were adapted for that. These are processes that are not Earth specific. This is what evolution will look like everywhere.
And I guess this might not be here nor there, but there could be worlds in which the mutation rate is significantly higher or lower than what we deal with here. We have all of the protective mechanisms that we have, yet we still have mutagens and we see cancer, but we also see like random flukes of evolution because of the amount of, mutation. That we see. But there could be worlds where the mutation rate is way higher and where we do see these very random big jumps in evolution that are somewhat less constrained. Or do you think that's a bit fantastic for me to ask?
Well, there's some good reason to think that big jumps are unlikely. Again,
Okay.
weird stuff's going to happen. There's going to be weird stuff around. But I think that in general, um, big jumps are unlikely to be to be very common because big jumps will tend to do more harm than good.
Right. They might
Um,
just kill off that lineage altogether.
Yeah, so this is
Yeah.
this is
Okay.
kind of a semi general or universal principle. But the truth is that until we know how creatures or organisms on another planet reproduce and how they pass that information from one generation to the next, then it's very, very difficult to draw conclusions about this. And the biggest example, the biggest question there is things like, well, will aliens have sex? Because sex has played a huge role in the diversity of life on Earth. But that's one thing that it's much harder to say, well, I think that's something that will exist on any planet with a complex ecosystem. That's a difficult question.
Right, because we even have examples where that's not necessary here. We have parthenogenesis in certain species, really complex species, which is pretty cool. We have, examples in plants don't have sex. Some plants have sex in their way, but other plants, they can literally just like rip a piece of their body off and then, boop, here's a new baby plant, and how cool would that be if animals could reproduce that way? And some low level, right, like planaria, like flatworms, you can kind of cut them in half and regrow two new ones. And so there are examples where the rules are already broken, even within our structure.
Yeah, but it's difficult. It's tough, and researching the origins and the role of sexa it's a really, really complicated subject. So those planarians that you talk about,
Hmm.
yes, you can cut them in half and they will regrow, but there are also planarians who reproduce with sexual reproduction.
Right, because otherwise
And
you don't have variation, right? Like if you're only doing budding, I guess you could call it, or if you're only doing parthenogenesis, like female birth to XX over and over, you end up losing that genetic diversity.
yeah, and remember that those organisms, even the flatworms, even the parthenogenic aphids, and even the parthenogenic lizards,
Hmm.
evolved as sexually reproducing
Yeah,
organisms. And they latterly began to reproduce asexually. So they would never have got to that stage if it hadn't been
right.
for sexual reproduction. And when you look at life on Earth, if you look at the truly asexually reproducing species on Earth, that's the bacteria, right?
Yeah.
We're not talking about flowers and animals and trees and no, those are all sexually reproducing. So there is a big question: are we talking about something fundamental here that we would expect to see on other planets? Something like sex, right? It's not going to be just like it happens on Earth, because what happens on Earth is all to do with DNA, and we don't know whether DNA is the molecule that's used on other planets, but
But a
something like
mechanism
that.
to shuffle their whatever their version of genes is going to be important. A mechanism to shuffle up the ingredients so that diversity continues.
Well, it may be, but then of course, don't forget that bacteria on Earth, although they reproduce asexually, they still
Yeah,
have
they're
horizontal
shufflers.
gene
Yeah, and they're
transfer. So there are
awesome at that.
mechanisms, yeah.
Yeah, yeah. Because otherwise, yeah, it would one really, really violent mutation that is the death knell for the entire species. And we have that happen too. We've seen that happen historically, but as they say in Jurassic Park, life finds a way. Oh God. Sorry. Um, so, we talked a little bit, and we're coming close to the end, but we talked a bit about movement, how important movement is to this story, about what we understand about animals on Earth, and how that may apply to aliens in other worlds. Can you maybe a quick and dirty about some of the other kind of fundamental principles that you in your work have observed throughout the animal kingdom that you think might be indicative or might be helpful for us to understand the alien sort of experience?
Well, the one I haven't talked about, of course, is the one that I work with the most, which is communication.
Right.
So once you have animals that need to interact in some way, either to mate or to come together for other reasons, then they have to communicate. There has to be some way of sending some kind of message between them. And what kinds of communications could there be? Well, it turns out that this is probably not like a too much of an Earth-centric assumption, but it turns out that sound is actually a really good way to send signals. I mean, it's what we're used to, but there aren't that many different ways. Sound is one. It works well if you have got a decently dense medium that you're in, a dense gas or a liquid.
Right.
Um,
Something that the waves can actually travel through.
yeah, I mean, it wouldn't work so well on Mars, for instance, which has a very thin atmosphere. But light works well if there's light. Okay.
And if the organism has an apparatus to receive
Well,
these
but
signals.
the organism will evolve. So one of the things about communication apparatus is that communication's always based on some kind of sensory organ. So we don't speak in sound because it's good. We speak in sound because we can hear. We evolved
Right, because
to
we have
hear
ears and
things,
yeah,
and then
yeah, yeah,
from the
yeah.
ears came the speech. So
Yeah.
you could imagine organisms in an underground ocean, for instance, where there's no light, that they might not have evolved light sensing organs, assuming that there's no organisms that generate their own light. And then in that case, they won't communicate using light. So
Right.
it all comes down to sensory. But there just aren't that many media for transferring information. There's sound, there's light, there's electricity, there's
There's
chemicals.
magnetism.
Yeah, magnetism's an interesting one.
Mhm.
We don't see organisms communicating using magnetism on Earth,
We
but
see
it's
them
possible.
navigating, sometimes
We
using it,
have
right? But
sensory.
not
Yep, we have them
yeah.
as with a sense of magnetic sensory
Mhm.
facility, but it's not evolved into a communicative facility. It's
Mhm.
probably just because it's a little bit difficult, but it doesn't mean it's impossible. Could be something on other worlds.
And even things that are kind of weird for us, like sonar, really, that's still just hearing, right? Or that's still like utilizing these sensory apparatus that are familiar to us.
Yes, and the perception. What's really difficult to understand is the perception.
Mhm.
It's not the sound. It's the idea of how you would form an image in your mind of what's around you from listening to the echoes that you generate. Um,
Right. But we've even seen at a very rudimentary level human beings with low vision managing some, rudimentary form of echolocation, which is freaking cool.
yeah, I don't think it's that weird of a sort of a sensory mechanism at all. But
Yeah.
it's that's another one that's just going to be very common. Evolved
Yeah,
many times on
yeah.
Earth. It'll evolve many times on other planets too.
Oh, I love that. It's so cool. So, movement, communication, basically these means of interaction, really. That seems to be what it comes down to. Very, very complex communication we might call language, and even beyond language, the development of alternative sort of forms of technological communication. But these are all variations on a theme that have a sort of I guess we could say not chronological. I don't know if that's quite the right word, but a temporal building. Over time, they've developed.
Yes, well, I mean, every trait
Right.
develops slowly over time. Okay, this is like we have our language evolved over the course of probably whatever couple 100,000 years or a couple 100,000 years or however long it took. We don't really know, um,
Yeah.
and sometimes things happen suddenly. We tend to think that language arose very, very quickly, but on an evolutionary timescale. I mean, we don't know how quickly, but probably extremely quickly compared to
Mhm.
other things. The dolphin sonar probably evolved much more slowly. The magnetic sensing in pigeons also probably evolved slowly. So things do evolve slowly over time, and then sometimes there's just a sudden innovation.
Right, but even those innovations are built upon mechanisms that evolved very slowly. Like, if we didn't have all of the architecture laid out and all of the capabilities for language to, like you said, innovate quickly, it wouldn't occur. We still needed all of those the slow evolution of those mechanisms.
And what's nice about that is it does tend to make those innovations fairly predictable.
Right.
You know what these organisms on another planet are going to have. They're going to have their legs, and they're going to have their sight vision and their sound vision. So you can make predictions about what kinds of things will evolve on top of those.
You're right. That's like the story of convergent evolution, right? Where we see these things crop up over and over without a similar lineage, simply because the constraints are somewhat predictive of flight, for example, or of, I don't know, fingernails, or, whatever actually fingernails is a bad example, but flight. Flight is a good example. Bats evolved flight, birds evolved flight. They did not evolve flight from one another. It's just that seemed to be a really good mechanism for both of those different lineages.
That's exactly right. That's really the I think you've summarized the thrust of the argument there.
Excellent. Then there's nothing more to do. Uh, so you know what, Arik, I'm so excited that we've been having this chat. I've learned an awful lot from you, and it helps me to organize my thinking as I go. So thank you for like bearing with me as I do that sort of reflection back. I ask all of my guests on the show the same two closing questions, and they're sort of big picture questions. And I was hoping that you might indulge us and take a go at these big picture questions as well.
I'm open. Shoot.
Kind of put you on the spot there. All right. So I want you to think about the future in whatever context is relevant to you. So, of course, in your work, you do this quite often. But this could be personal. It could be universal, whatever. We could go from the cosmic all the way down to the individualistic. And I want you to tell me first, what is the thing that really is keeping you up at night recently? The thing that you are most concerned about? Maybe you have even some like pessimism or cynicism that's brewing. Where are you finding your worry? And then on the flip side of that, to sort of end on a more positive note, where are you able to tap into a very authentic and real optimism? Like, what are you looking forward to?
Well, I do teach a lot, and I work with
Mhm.
students a lot, and I think that this is really probably the answer to most of your questions. So on the downside, I see that the human race has not got its act together. We haven't got empathy. We just don't seem to have figured out how to care about what happens to other people, and that keeps me up at night. And I think that's driving all the stuff that should be keeping people up at night, like climate change and so on. But I think a lot of it comes down to this inability or this difficulty that we have really to care about what happens to other people. But as I said, as a teacher and as someone who works with young people and young students, and I see such a drive and such a rush and enthusiasm for making things better and for learning more about life and for learning more and respecting the life in the universe. And I work with such a fantastic group, my research group of mostly of younger people, such a powerful force for change that exists when people get together and start saying, well, actually, this is really interesting. Let's go try and fix this and find out about this. So there is energy there. It just needs to be channeled into the right direction, into that empathy, so that we can solve the real problems that we're facing.
I couldn't agree more. Well, Arik, thank you so much for spending the time today. Everybody, the book is The Zoologist's Guide to the Galaxy: What Animals on Earth Reveal About Aliens and Ourselves. It was an absolute joy.
It was such fun talking about it.
And everybody listening, thank you for coming back week after week. I'm really looking forward to the next time we all get together to talk nerdy.